Good evening. My name is James and I'd like to welcome you all to Skeptics in the Pub online. I'm coming to you live from just outside the actual definite Garden of Eden, as proven by the Panacea Society right here in Bedford. But we've got people from all over the world and we'd like to welcome you to this talk. Every second and fourth Thursday of the month, we gather together as a little refuge from the world of nonsense that's out there to discuss scientific or skeptical or just generally interesting talks. But it's not just online nowadays. After what's all been going on, there was a hiatus for a while for many of our in real world groups, but we've started getting back into the real world now. Take a chance to look, see if there's a Skeptics group near you. For instance, I happen to know there's one near me, the Bedford Skeptics in the Pub group, who have a talk coming up on tackling climate change and the sixth mass extinction with Professor Jim Harris. So if we're doing one, there might well be a talk near you. And if you like seeing skeptics in real life, we've got a special treat for you as well. For years, there's been an annual gathering of the skeptics in Manchester, the QED talks, the QED conference, my apologies. That is running on the weekend of the Friday the 28th of October. Almost got that wrong. And as a special treat, the organisers of the Skeptics in the Pub online gatherings will be running something called Skepticamp on the Friday evening. That's short talks of a more less formal nature, perhaps. And we are still looking for applicants who want to present at this event. So check out the QED website. There is information on that in the chat, which is over there, actually not down there. There's information in the chat that will come up for that information. The QED conference looks like it will be fantastic. There are some amazing talks and some amazing panels and live podcasts. It's something I'd love to see as many of you there as possible. Unfortunately, we know that not everybody can afford a weekend in Manchester these days. The world isn't as easy as it used to be. The world isn't as easy as it used to be. But we have had a project running where we have been gathering donations to help people who haven't necessarily got the funds to attend the conference themselves. Applications for that help is now closed, unfortunately, but we do still want your help to fund as many people as we can to come to Manchester. We want to see as many of you there as possible. In the chat, and I believe down below me here, there is a link to SITP online /donate. Any donations we get today will go to this fund that will help people that can't afford to come to Manchester to come and see us and see the rest of these talks. And we want as many people as we can help to go to that as possible. The final bit of admin is the Skeptic magazine, which is now being run by the Merseyside Skeptic gang, who are well known to most of us, I believe. They do an annual Occam's Razor Award. That's the chance for you to nominate who's done the best in skeptical work in the last year. Previous winners have included the Skeptics in the Pub online people and people who have done work promoting good scientific interest in COVID research and fighting against bad COVID research. There's also a chance to nominate someone for the Rusty Razor, which is exactly the opposite of that. Someone who needs pointing at and denigrating a bit for the bad work they've done in their bad science communication in the previous year. So that's the admin stuff. So now let's talk about today's talk. I can say without much uncertainty at all that today's talk will definitely not be a bore. I'm fairly certain that there will be a big sigh of relief because this talk has the potential, well, more than the potential. It has the absolute chance of being a fantastic talk. We're going to be learning from Dr. Steve Barrett, who is a senior research fellow in the Department of Physics at the University of Liverpool. His research has included the applications of imaging and spectroscopy to many sciences, such as nanoscience, geomaterials, medical imaging, and infrared spectroscopy. But today he's going to be talking about the world that's a lot smaller than we might be used to. The concepts that underlie quantum mechanics seem to make no sense. We're a species that was evolved to be able to recognize scary lion, tasty apple, but somehow we've developed the tools to describe the universe on the tiniest possible scale. And so now I'd like you all to be incredibly welcoming to our guest for today, and that's Dr. Steve Barrett from the University of Liverpool. Thank you very much.
And good evening, everybody. It's great to be here to talk to Skeptics in the Pub online. So this is the weird world of the very, very small. I'm going to be introducing the idea of how quantum mechanics quite often goes directly against the ideas of common sense. So we're going to be looking at a sense of scale, going from the everyday down to ultimately nanometers, and a sense of symmetry to see how we can get an idea of what the world is made of. And we'll look in the quantum world ultimately at individual atoms, but along the way we'll see that our understanding of the quantum world doesn't always agree with our understanding of common sense. So I guess we're all familiar with the world on the scale of kilometers or meters or down to even nanometers. Correction, down to millimeters. That's the sort of scale that we can easily understand. That's the sort of scale that we can see. At a push, we might be able to go a little bit smaller than a millimeter. Perhaps you recognize one of these structures. This is only some 1/10 or 1/20th of a millimeter in diameter. This is a pollen grain, and arguably it's about the smallest thing you can hope to ever see with your naked eye, but of course an easy object under a microscope. We can build, certainly on smaller scales, we can build mechanical objects on scales down to tens of microns if we wanted to, just a fraction of a millimeter or so. But of course, it's in the world of electronics that we've really taken this to the limit. These days, a microprocessor chip might have an area of a few square millimeters, perhaps even a square centimeter, and there could be 100 million or perhaps even a billion transistors on board a microchip. So that means the individual components that we are building these days, the components are of order 10 nanometers or so in size. We are getting very close to the point where we can ask, well, can we go realistically, can we go any further and build anything on a scale smaller than about 10 nanometers or so? So we can ask ourselves, what is the world made of? And we can ask ourselves, well, how do we tell what the world is made of? What clues do we have that help us understand how the world is put together? Aristotle thought about this and came to the conclusion that everything is made of the four basic elements: earth, air, fire, and water. Wouldn't it be great if that was actually true? That would be really nice and simple, just four elements in the periodic table. Everything is made of just combinations of those four. But some centuries later, it was realized that we need to take a slightly more critical view of how the world is put together. And it was Galileo who really tried to convince us that the nature of the world around us should be determined by quantitative experiments, not by simple qualitative intellectual arguments. In other words, we shouldn't be asking what should happen or how would we like it to happen if something was the case. We should be asking what actually happens, not how would we like the world to be made up, but what is actually the constituents of everything we see around us. And sometime later, Newton took this to the next level and basically came up with his laws of motion, law of universal gravity. He did experiments on the nature of light and established what we now call either Newtonian mechanics or perhaps classical mechanics. the mechanics that existed before we had this confusing period of so-called modern physics of the last century, where everything started to get overturned. So in the days of Newton, we would think that everything is well understood and the universe is basically a beautiful clockwork universe. Everything works the way it should. We're not making any comment about how the universe came into being, but now that the universe is running, and we mean the universe in the most general sense, the world, the Earth, the solar system, everything beyond the solar system. Everything seems to work by clockwork. Everything is deterministic. If we know where Jupiter is now, if we can measure it accurately enough, and we understand the laws of gravity, etc., then we can work out where Jupiter is going to be in a year's time, or 10 years' time, or 100 years' time. In principle, if we can measure Jupiter's position accurately enough, then we can measure its position, we can determine its position for any period in the future that we wish. And if we wish, we can dial the clock back and work out where the planets used to be in the past. So a beautiful clockwork universe. And using that idea, we can say, well, does that tell us what matter is made of? For instance, if we look at snowflakes, they all appear to be different. We're told everyone is different. But if we look at snowflakes, they all have a particular pattern. They all have six-fold symmetry. So surely that must be telling us something about the nature of what makes up a snowflake. What are the building blocks? What is the smallest Lego brick that we can think of that we can use to actually build a snowflake? Must these Lego bricks be six-sided in order to explain the fact that we always get six-sided snowflakes? Well, we can look at lots of different materials. For instance, when metals melt and then cool down and recrystallize, they produce all sorts of weird and wonderful shapes. Again, whatever the building blocks are that make up these materials, there must be some clues in the particular shapes that they choose to adopt. And so if we look at materials that seem to prefer to be this sort of cubic or cuboid shape, does that mean that in this case, the building bricks are little cuboid Lego bricks, little cubes themselves? And of course, if we put lots of cubes down, we can then build these various structures. But it would be nice if all the building blocks were the same, rather than have a different building block for every material, all of the thousands, tens of thousands, millions of different materials in the world around us. We don't particularly want to have a different building block for each, because that gets very complicated. We want something similar to the Aristotle view of there's only 4 elements and different combinations will produce the structures we want. So in that particular case, it looks like the building blocks are likely to be little cubes. But how can we then explain the fact that some materials decide to crystallize into a dodecahedron? Surely if they do that, that can't be the result of lots of little cubes getting together. Why would little cubes produce a dodecahedron? There must be something going on, whatever this smallest building block is, what Democritus used to call an atom. If we take a material, cut it in half again, is there a limit? And if we call that limit an indivisible, an atom, then are these so-called atoms a particular shape, and how can we possibly explain different shapes of crystals? So we look around the world and we realize that the shape and symmetry of macroscopic crystals must be telling us something about the underlying structure. But simply looking at those crystal shapes doesn't tell us what these fundamental building blocks are. Now, throughout 300 years, from 1600 to 1900, there's Democritus on the left-hand side, clearly out of position. He should be way over beyond the left-hand side of the screen. But during these 300 years, from 1600 to 1900, there were a number of key players who started to put together the picture of, well, if the world is made of indivisible Lego bricks, what are those Lego bricks that we are now going to call atoms? Perhaps you recognize some of these individuals. Let's go and put some labels on them. There's Boyle, there's Newton, of course, and then to the right is Lavoisier. In 1800, we have Dalton and Avogadro, and on the right-hand side, we have Maxwell and Boltzmann. All of these individuals made a contribution to our understanding of atoms. I'm not going to make this a history lesson of what they all said, but a lot of the work in these centuries was based on the idea of chemical reactions. If this chemical compound interacts and reacts with this chemical compound and produces this result, when we look at the masses involved, we get the impression that if there were building blocks of a particular size, a particular weight, a particular mass, then it looks like we can explain lots of different compounds producing lots of different reactions if we simply start with a number of basic building blocks. Probably more than 4, but probably not an infinite number. So this idea of, yes, there are fundamental building blocks called atoms, and we need to understand the nature of these atoms in order to understand exactly why we get certain chemical reactions. In between 1800 and 1900, there were a couple of key observations, a couple of key experiments that moved us further. In the early 1800s, Thomas Young established that light is a wave. In previous centuries, we weren't quite sure. Newton was thinking about whether light was a wave or light was a particle, a corpuscle, as the term he used at the time. But Young showed that different light sources produce light that interferes, and interference is a wave-type phenomena. So if light can interfere with itself, then light must be a wave. So it was established in the early 1800s that light is a wave. Later in the same century, J.J. Thomson discovered one of the particles that are fundamental to our understanding of atoms. He discovered the electron, a negatively charged particle. So in this particular century, we have a nice simple situation. We know that light is a wave, and we know that electrons are particles. Electrons can't be the whole picture in terms of the atoms that we're looking for, because we know that electrons are negatively charged, and if we have a bunch of electrons together, they will all repel each other. So given that we are aware of the fact that on a macroscopic scale, matter doesn't seem to have any net charge, if we know that electrons exist and they have a negative charge, then presumably there must be something else that we're missing, another set of particles that have a positive charge, such that in total, atoms, and hence we, have a net neutral charge, a net zero charge. So everything looked reasonably hunky-dory in the 1800s, with the exception that we haven't found these positively charged particles yet. However, the next century, well, everything got turned upside down. Notice the scale here is not the entire set of the 1900s, it's only the first 3 decades from about 1900 to 1930. But so much happened in these 3 decades that it's worth just concentrating on what happened up to this point. Again, some of the key players here, their photographs are simply put onto this timeline approximately in the positions where they made the greatest contribution. And again, maybe you recognize some of these faces. Let's go through them. Becquerel, and then Max Planck, and then we have Rutherford, and then of course everybody recognizes Einstein. Then we have Niels Bohr, we have de Broglie, and on the right hand side we have Heisenberg and Schrödinger. A number of different observations and theories were put forward during these 3 decades. But some of the key points, I'm not again going to turn this into a history lesson, but some of the key turning points to our understanding are indicated on the bottom line here. So the discovery of radioactivity. In most of the cases, these red markers don't necessarily correspond to just one person. For instance, the idea that light is actually a particle was pioneered by Planck and then used by Einstein to explain the photoelectric effect. In the next few years, the idea of atoms, and in particular the discovery of the atomic nucleus, that was a key turning point when it was now realized that an atom has got a positively charged nucleus plus negatively charged electrons. So our picture of the atom is not quite complete at this stage. It's a couple of decades or so before the neutron is discovered, but the idea of positive and negative charges making up an atom is now established as of the first decade or so into the 20th century. The other key point which changes our understanding of the nature of atoms is the idea that it is not a deterministic system. We can only talk about probabilities. Now, not everybody was happy with this idea. We'll come to that point a little later. But basically, we can only talk about the probability of something existing, or the probability of an event taking place, or the probability of an electron having a particular position, or a particular speed, or a particular energy. That is absolutely fundamental to what ultimately became the theory of quantum mechanics. And the final nail in the coffin, if you like, is the confusion wrought by de Broglie, who said that electrons are not particles, they're waves. So remember, in the previous century, it was established as fact that light was a wave because we can get wave interference, and electrons are particles. And now, effectively only a few decades later, we've now completely turned that around and said light is a particle and electrons are waves. So this is the basis of what became known as wave-particle duality. Ultimately, we shouldn't really be talking about particles and waves, because stuff, the nature of matter, what we are calling atoms and the fundamental constituents of atoms, strictly speaking, are neither particles nor waves. They have particle-like properties and they have wave-like properties. It was often said that they behave like particles on Mondays, Wednesdays, and Fridays, and they behave like waves on Tuesdays and Thursdays. What they do on weekends, nobody seemed to actually know. But this idea of wave-particle duality, that some things behave like waves and behave like particles, sometimes at the same time, even more confusingly, and the fact that we can't really talk about definite things with certainty, we can only talk about probability. All of these ideas were thrown into the ring, and it was Heisenberg and Schrödinger as the main architects of quantum theory who took all of these various strands that were put together by these various luminaries from the previous few decades and came together to produce the idea that we now call quantum theory or quantum mechanics. Heisenberg and Schrödinger took different approaches to how they tried to construct a mathematical, self-consistent mathematical construct which bound together all of the ideas and all of the observations that had been made up to this point. Heisenberg and Schrödinger took different mathematical routes, but ultimately it was realized that they were describing the same thing. They were just using slightly different mathematical tools to come to effectively the same conclusions. So quantum mechanics appears to describe the way the world is on a scale of the very, very small, meaning the scale of much smaller than us and approximately the scale of atoms and molecules. There doesn't seem to be a hard dividing line where we say we give up on quantum mechanics and bring Newton back into the driving seat and say if something is larger than this, then we don't need quantum mechanics. There is a very blurred boundary between the two. But as of the early 1930s, it was established that the way we understand how atoms work and how atoms make molecules and molecules make us, the only way to describe this is a mathematical theory called quantum mechanics. The quantum of quantum mechanics comes from the observation that when we put atoms together, if we use Newtonian mechanics to explain how atoms behave, it doesn't work. We must have a particular restriction on how particles behave in atoms. We can't have electrons and the nuclei of atoms doing whatever they like. Their positions, their motions, their momentum, their energies must all be quantized. If we don't quantize, if we don't specify that they can't have any value they like, but they can only have these particular values of angular momentum or these particular values of energy, only then do we get the theory to agree with observation. So that is why ultimately it became called quantum theory. So this is the picture we would like to have. Everybody has this picture in their heads, whether they admit to it or not. Everybody would like an atom to look like this. A nucleus. It's made up of positively charged particles and, as it happens, neutrally charged particles, neutrons. They were discovered just after my timeline there in about 1932. But we have a positively charged nucleus and buzzing around it negatively charged electrons. And that's a nice, very pretty picture. But it's wrong for a number of different reasons. Not least because it doesn't tell us that all the electrons actually have different energies. Various electrons in an atom have to have different energies because that's one of the rules of quantum mechanics. So a better picture would be one that looks a little bit more like this. We've got what appear to be electrons going around a nucleus, and we have more than one electron in the first orbit and more than one electron in the next orbit and more than one electron in the next orbit. So it's a little bit like a solar system, but we have multiple electrons in each orbit, and the number in each orbit are very strictly controlled. We have 2 in the first one, then we have 8 in the next one, then we have 18 in the next one. I'm not going to describe where those numbers come from, but they are fundamentally embedded into the theory of quantum mechanics. They're fundamentally embedded into the way the electrons are quantized in the atom. So we shouldn't really be thinking of it as a 2-dimensional solar system. It's actually more like a set of 3-dimensional shells, as indicated by the bottom part of this diagram. But it's unlike a solar system, not simply because it's not 3-dimensional, and not simply because we don't have, for instance, 2 Mercuries going around the sun and 8 Venuses going around the sun and 18 Earths going around the sun. The key difference is not those trivial differences, it's the fact that we can only describe atoms by thinking about probabilities, whereas when we think about the solar system seems to behave according to the rules of a clockwork universe. So once we've got these electrons in various orbits, as determined by the quantization rules, then that explains, because we have 2 electrons in this shell, or this orbit if you like, and 6 in this one and 18 in this one, that explains why we have the periodicity in the periodic table of elements. There aren't simply 4 elements that make up everything, earth, air, fire and water. It's not just 4, it's more like 92. Plus a few we can make ourselves as well. But essentially, as far as we can tell, everything is made of those 92 elements. And we can understand the properties of those elements because the properties of the elements are dictated by the way the electrons are arranged in these orbits around the nucleus. So quantum mechanics enormously successful in explaining why we have 92 elements in the periodic table and what their properties are. But we have established that we shouldn't really be thinking of an atom as a solar system. We shouldn't really be thinking of, well, electrons are just like satellites buzzing around the Earth, aren't they? Well, no, they're not, for a lot of different reasons, not just the trivial ones of it's 3-dimensional, not 2-dimensional. The solar system is almost 2-dimensional. Everything is pretty much planar. But it's this idea of absolute predictability versus probability that's the key difference. When we're thinking about where an electron is in an atom, we can't say, unlike Jupiter in the solar system, we can't say the electron is there now and I know how fast it's going, so in another nanosecond that electron is going to be over here. All we can really do is to say, well, if I've got an electron in a particular state in an atom, then I can say, how likely is it that I find that electron at a particular point relative to the nucleus? So here we have 8 different pictures, and if we take this first upper left picture, you can imagine the nucleus is at the center of this picture. It's not actually shown, and the gray here, the brightness of the gray smudge, the brightness of the gray cloud, is an indication of how likely we are to find the electron at a particular position. And you can see that it's relatively simple for this first electron, but other electrons can exist in states. Look at the bottom right, for instance. Again, there's the nucleus right in the center. But look at how complex the pattern is when we ask, where are we likely to find the electron? If we were to try and measure the position of the electron, what's the probability that we find it at any particular location? And the answer is a very complex pattern which can be predicted by quantum mechanics, but is very counterintuitive. So when it comes with the problem of dealing with atoms, we can try and say what atoms are using words. We can talk about particles and waves, but we've already said that that's very confusing because particles are waves and waves are particles, or at least those words don't have the meaning that we associate them with when we're talking about everyday life. And when we're talking about an electron in orbit around a nucleus, it's not really in orbit around the nucleus in the same sense that the Earth is in orbit around the sun. And we can't even talk about electron spin and think of it as the same thing as the Earth spinning, because we're using the word but in a different meaning. We're having to reuse words because there are a finite number of words in the English language. Words don't work when it comes to describing atoms. So you say, okay, let's forget words, let's just deal with pictures. But we've already said that pictures of electrons orbiting a nucleus are not strictly speaking correct. It's a little bit closer to think in terms of probability clouds of electrons around atoms, but even that, strictly speaking, doesn't capture all of the essence of an atom. So what should we do if words don't work and pictures don't work? What is the correct way to describe the weird world of the very, very small? How should we be describing atoms? Well, I'm afraid there's only one option, and most people don't like it, because the only way we can really describe atoms is with maths. And quantum mechanics tells us this is the maths you need to use, not just that equation, but that's the basis of a lot of quantum mechanics. If we can solve that equation, then we can understand how things behave. We can predict what we're going to get if we make a particular observation in a particular experiment. But the catch is the maths isn't particularly easy. Don't take that equation at face value. It's much more complex than that. And if we want to describe the maths, for instance, if I wanted to teach this maths to a student, I can't just throw the maths at them. I have to use words to describe what I'm doing. And where possible, I use pictures to describe what I'm doing. Humans are visual animals. We can understand things better if we can picture, if we can visualize them. So even when we know the picture is wrong, we will still use pictures to try and help our English explanations of what the maths is trying to tell us. And therein lies the problem. That's the sort of maths we have to deal with. This is somewhere in the middle of university quantum physics. It's probably a mix of first and second and possibly third year maths involved in trying to understand the nature of waves, the nature of particles, the nature of atoms. It is not the sort of stuff that gets taught in primary school. And there lies the rub. We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language. This is Heisenberg making it clear that he's put together or helped put together, he's one of the prime architects of quantum mechanics, but he realizes that the maths works, but we can't talk about atoms in ordinary language because ordinary language is not built to talk about atoms and the world of the very, very small. So you could say, would it be better to use words that don't carry any preconceptions, any baggage? Rather than say electrons orbit and spin in the atom, would it be better to say the slithy toads did Gaia and Gimbal in the wave? Because both of those red sentences carry exactly the same amount of information. The first one doesn't mean anything until you define what do you mean by an electron, what do you mean by an orbit, what do you mean by spin, and what do you mean by atom. You have to understand the meaning of all of those before that sentence makes any meaning. And the same is true of the second one. So had we thought about this 100 years ago, perhaps we should have chosen words that didn't come with baggage, and we could have chosen a whole set of new words that only exist in the context of quantum mechanics. But we didn't. We tried to be clever by saying we can explain this in terms of orbits and spin and particles and waves, and unfortunately, the words get rather mixed up. Bohr had this comment: everything we call real is made of things that cannot be regarded as real. That's a pretty amazing statement. We're made of atoms, but atoms aren't real. So does that mean we aren't real? At what point does reality kick in if the atomic world is not really real, but is just a mathematical construct? At what point, when we build atoms into molecules and molecules into us, at what point does reality kick in? Schrödinger's comment: atomic physics has shown that atoms have no meaning, but can only be understood in experimental measurement. That is a quite incredible statement for a physicist to make. What he's really saying there is that quantum theory is a mathematical construct which successfully allows us to predict anything we like in terms of an experiment. If we ask, what energy will this electron have in this hydrogen atom, we can calculate that and we get an answer, and lo and behold, quantum mechanics appears to give the right answer. We can ask, for this particular molecule made of lots of different atoms, what are the properties of this particular molecule? How should it behave? We can plug that into quantum theory and it can give us the answer. But Schrödinger's comment was that atoms themselves have no particular meaning. They are just a convenient way of calculating what it is you measure when you do an experiment. So you could argue this is philosophy. Does that mean atoms are real, or does it just mean that we have a convenient way of describing how the world actually works? I don't like it, and I'm sorry I ever had anything to do with it. This is the prime architect of quantum mechanics saying he doesn't like what he's created because he doesn't like this problem of quantum mechanics giving you all sorts of answers which might be correct in the sense that they correctly predict experiments, but trying to interpret what they mean is quite a headache. For instance, let's look at quantum mechanics where it disagrees most violently with common sense. Atoms are unpredictable. We've said that basically everything on the small scale only obeys the rules of probability, not determinism. So we can only know the probability of an atom having a particular position in space, a particular speed, a particular momentum, a particular energy. We cannot say that this is the case. We can only say what is likely to happen in the future, and we can calculate those probabilities, and then we can do the experiment to see what actually happens and see if that fits with our understanding of the probability of things happening in the future. And although we think of atoms as being very small, this is the weird world of the very, very small, strictly speaking, atoms do not have a finite size. From what I've said in the first statement there, an electron could be anywhere. The probability of an electron being close to the nucleus of the atom it's in is quite high. An electron is quite likely to be within 1/10 of a nanometer or so of the nucleus. If we were to measure it, that's where we're likely to find it. But there is a finite probability it could be much further away. There's a finite probability the electron is 1 nanometer from the nucleus, or 10 nanometers, or 100 nanometers, or a millimeter. There's a finite probability that the electron could be in Australia, or could be in the Andromeda galaxy. It is a vanishingly small, or not quite vanishingly small, it is a tiny, tiny, tiny probability, but strictly speaking, that probability never actually goes to zero. It simply goes to smaller and smaller, smaller values asymptotically. So if you ask the question, how far from a nucleus do we have to go before we are guaranteed that the electron is in there somewhere? The answer is, well, the size of the universe. We can, of course, say, well, the chances, the 99% probability limit, the chances that it's 99% that we find the electron within a given sphere, we can make that sphere fairly small because the probability does fall away. But strictly speaking, it never goes to zero. And one of the areas where it completely goes against common sense is the idea that atoms can be in two states at the same time. In other words, an electron can spin clockwise and anti-clockwise at the same time. Clearly, that does not happen with the Earth. The Earth is spinning on its axis and is going around the sun, and depending on which way you decide is up or down or north or south, you can define which way the Earth is spinning. But it doesn't spin both ways at the same time. If I toss a coin in the air, it spins in a particular direction. If I spin a coin on the desk, it spins in a particular direction. Doesn't necessarily mean I know whether it's going to be heads or tails, but the spin direction is a particular value. Whereas when we're talking about atoms and subatomic particles, they can, in principle, be in two states at the same time. And again, that is fundamental to our understanding of quantum mechanics. Why does quantum mechanics disagree with common sense? Common sense is the collection of prejudices acquired by age 18. In other words, common sense is what we've built up in 18 years of a life as a child before we become an adult. And at that point, common sense is the sense we need to make sense of the world. We look at the world, we try and make sense of it. Common sense is just the things that we know will happen. If I pick something up and drop it, it will fall to the ground. I know that because I've seen it happen thousands of times. That's what common sense is. But if quantum mechanics disagrees with common sense, well, one of them must be wrong. And whenever quantum mechanics disagrees with common sense, it's common sense that's wrong, not quantum mechanics. And accepting that is sometimes very difficult. If we were to toss a coin, the question is it heads or tails? If we toss a coin and then put it onto the back of our hand, we say that, well, it's either heads or tails, and I won't know until I look at it. But quantum mechanics says, no, it's heads and tails until the experiment is actually carried out. But certain people like Einstein didn't like this idea. They didn't like the idea that the universe is essentially probabilistic rather than deterministic. God does not play dice, he says. God is subtle, but he is not malicious. Other people believe that the universe quite definitely is probabilistic. So in response to Einstein saying God does not play dice, Bohr retorted with, stop telling God what to do. In other words, the universe behaves this way. Deal with it. That's the way it is. You may not like it. You may not like the idea that quantum mechanics deals only with probabilities, but quantum mechanics, as far as we can tell, is the correct way of describing the universe. So we might be missing something, but as of yet, this is the way the universe works. Let me deal with three aspects of quantum mechanics, which reveals some of the weird aspects that I'm talking about. The order in which things are done, then Schrödinger's cat, and then we'll look at how we actually see atoms. So firstly, order. Now in algebra, we know that A times B is the same as B times A. Everybody knows that 2 times 3 is the same as 3 times 2. Really doesn't matter which order you put things in. However, in quantum mechanics, A times B is not the same as B times A. In this context, A and B refer to, for instance, making a particular measurement. Let's say I'm interested in looking at this atom and I want to know what this electron is doing, and I'm interested in the position of the electron, and I'm interested in the speed or momentum of the electron. So why does it matter that in algebra the order doesn't matter, but in quantum mechanics it does? Well, we can do a little thought experiment and say, what if the rules of quantum mechanics actually applied not just to electrons and atoms? What if they applied to macroscopic scale things, such as, for instance, what if it applied to a selection of animals? Let's imagine I go to Africa and I look over the plains and I see 4 groups of animals. I see lions and vultures and waterbucks and ostriches. So the top pair are carnivores and the bottom pair are vegetarians. So I can split them into the lion and the vulture, who are both carnivores, and the bottom pair, the waterbuck and the ostrich, are both vegetarians. But if I wished, I could split them a different way. I could say for those 4 animals, the left-hand pair have got 4 legs, the lion and the waterbuck, and the right-hand pair of animals have got wings. Yes, I know the ostrich doesn't fly, but it still has wings. So those four animals can be grouped together in different ways. So let's imagine I wanted to split these animals up, and I wanted to split them up so that I could isolate just one of those four sets of animals. Let's see what happens. Let's pick two out of the four to start with. Let's pick out the vegetarians and move them to a different part of the grassland, a different pen, if you like. So I'm going to take the vegetarian animals and move them to one side. So I'm going to take the veggie animals, the waterbuck and the ostrich. Now that I've got these vegetarians on one side, I'm going to pick again. And now I'm going to pick the four-legged animals out of the pair that I've just chosen. So having selected the waterbuck and the ostrich, I'm now going to pick out the four-legged animals. And I would, of course, expect to find that I've just got the waterbuck. But if the rules of quantum mechanics apply rather than the rules of common sense, what I actually find is that I end up with the waterbuck and the lion. Even though I had selected the vegetarians in the first place, and then selected the four-legged animals, somehow the lion ends up popping back into my selection, even though I had separated out the waterbuck and the ostrich, and the lion was not there. When I pick out the four-legged animals, by some means or another, the lion reappears. This is perfectly okay within the rules of quantum mechanics, but it doesn't make any sense in the macroscopic world. Not only do I not get the result that I expected, but if I reverse the order and say, right, this time I'm going to pick the four-legged animals and put those to one side, and so the four-legged animals gives me the lion and the waterbuck. Now that I've got the lion and the waterbuck separated out to one side, I'm going to split them down the middle and pick out the vegetarians out of all of those. So out of the lions and the waterbucks, I'm going to pick the vegetarians, so I expect to get the waterbuck. No, I find I end up with waterbuck and ostrich. It's as if the second selection somehow has managed to scramble my first selection. Even though I make one selection and separate them out and then make a second selection, somehow that second selection has scrambled my knowledge of the first selection. That is how quantum mechanics works. And when you think of it on a macroscopic scale, selecting animals or selecting socks from a sock drawer, it makes no sense whatsoever. What about Schrödinger's cat? Let's take a cat and have a 50-50 chance of killing the cat. Now that's a bit worrying for certain felines, but let's not worry. This is only a thought experiment in which we're going to put a cat in a box and then we're going to contrive some weird and wonderful way of killing the cat. In this particular cartoon, what we have on the left-hand side is a radioactive particle, and we are going to wait for a certain length of time until there's a 50-50 chance of that radioactive particle decaying, which is then detected by this Geiger counter, which then sends a signal to this robot, which then smashes with a hammer this vial of poison, at which point the cat, who is apparently now sweating. I'm not sure cats actually sweat, but there we go. This cat, with Schrödinger on looking here, will either die or not. So the point is there's a 50-50 chance that the cat will die as a result of doing this experiment. But the point is we're going to put this experiment in a box and we are not going to look in the box yet. So if we wait a length of time until it is 50-50 chance that the cat has died, what is going on inside the box? Common sense tells us, well, the cat will either be dead or it'll be alive, and we won't know until we open the box. Quantum mechanics says something quite different. Quantum mechanics says, well, just like a fundamental particle or an atom, the cat can be in two states at once. Before we open the box, it's not simply a question of we don't know which it is. The cat will be in a so-called superposition. It'll be in both states at the same time. If it's possible for an atom to be in two states at one time, and we link the fate of the atom to the fate of the cat, then by logic, the fate of the cat must be it is dead and alive at the same time. When we open the box, then the state of the cat changes, and then it will become either a dead cat or a live cat. But before the box is opened, the cat is dead and alive. makes no sense whatsoever, but that is the way quantum mechanics appears to tell us the world is put together. And trying to make sense of that and trying to link the quantum world to the macroscopic world is still a problem of interpretation. The maths tells us one thing, but are we interpreting the results the right way? So how do we know quantum mechanics is right? Well, we don't know it's right. It's been around for 100 years, and so far nothing has proved it wrong. In other words, the principle of falsification, you set up the theory and then you try to tear it down. For 100 years, people have been trying to prove that quantum mechanics is wrong, and nothing so far has proved it's wrong. In all cases where quantum mechanics is able to make a clear prediction and we do an experiment, it gets it right. So, doesn't prove that quantum mechanics is right, but until we find something better, it is the best theory we have to explain the world of the very, very small. Quantum mechanics quite definitely can predict results that are impossible by good old-fashioned Newtonian classical mechanics. So we know that classical mechanics fails, quantum mechanics comes to the rescue and works. Maybe there's something else waiting in the wings, but we don't know what that might be. And rather surprisingly, one way we can use quantum theory is we can use a quantum effect to actually build a microscope that allows us to see atoms. A so-called scanning tunneling microscope, or STM for short. What we do is to bring a sharp tip into close proximity to a sample. Here I've shown a sort of pyramidal shaped tip coming close to a slab, and I've indicated a few of the atoms that will be at the very tip of the pyramidal structure and a few atoms on the surface of the sample. What we do is apply a voltage between them and measure the current that flows. Well, according to classical mechanics, if it's an open circuit, as indicated here, if it's an open circuit, no current will flow. But according to quantum mechanics, even though the circuit is not a closed circuit, it is possible for electrons to make it from the tip to the sample, or from the sample to the tip, depending on which way round the voltage is. Classical mechanics says it should be impossible for the electron to exist in between the sample and the tip, and yet quantum mechanics allows a current to flow. And the reason this is useful is because the amount of current that flows, although it's a relatively small current, it is very sensitive to this quantity I've labeled d, the distance between the tip and the sample. So if we have a particular topography of a sample and we move the tip over it, in other words, we scan the tip across the sample, we either measure the current that's flowing or we try and keep the current fixed, which means keep the distance fixed, in which case the tip will then map out the topography of the underlying surface. So we move the tip and measure the current and either use that in a feedback loop or just measure the current and then plot out what the current actually is. And we have a scanning tunneling microscope. We have quite a few of them. Most universities do these days. And the STM itself is sealed inside an ultra-high vacuum vessel, typically, in order to keep the microscope itself and the surface that you are trying to scan, to keep those scrupulously clean. So it is not that uncommon to have the scanning tunneling microscope inside a vacuum vessel that's kept at a pressure of about 10 to the minus 13 atmospheres. That excludes enough air that your sample stays clean for long enough for you to scan the surface. And here's an image courtesy of the University of Manchester from some years ago, in which they scanned the surface of iron oxide. You can see the scale in the bottom left there, 2 nanometers. So each of these little mountains that you can see here are individual atoms. You can tell that from the scale of this being 2 nanometers. But notice that the atoms aren't uniformly spread over the entire surface. The atoms appear to cluster in these little islands in a particular structure, apparently a hexagonal structure. But notice also that the islands themselves are arranged in space on a particular grid pattern, and there's particular regions in between them that look a lot smoother. And we can use these scanning tunneling microscopes to get a much better idea of how atoms and molecules behave by looking at the interactions of atoms and molecules on a controlled surface in order to have some control as to exactly how they behave, what atoms exist. We place atoms in certain positions and observe how they interact with each other. When we do this, we find that not only do we find certain atoms in certain materials or certain metals or certain alloys or semiconductors have particular arrangements in space. For some particular materials, we find some unusual arrangements. So, for instance, they don't necessarily group together in rectangular or hexagonal arrangements. In some metallic systems, they actually arrange themselves in pentagons, as you can see here. And that, of course, gives us a clue as to why those metals decide to crystallize as dodecagons, or dodecahedrons, rather. We can see that the fundamental arrangement of atoms on the smallest of scales gives us the reason why they arrange themselves on macroscopic scales here of quite a few millimeters into particular shapes. It's also interesting to note that if we were to measure the distances between these various blobs here, individual atoms, it doesn't matter which particular atoms we're talking about in this particular metallic compound, but if we measure the distances between atoms, we find that if we measure distances and take ratios, a particular ratio keeps cropping up in these particular metallic alloys. That ratio is the golden ratio, which is indicated by phi or sometimes tau, 1.618, blah, 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 blah. Not only do we see that at the atomic scale, we see that golden ratio cropping up at macroscopic scales as well. For instance, if you were to look at the number of scales on a pineapple going in one direction of its spiral structure and going in another, if you take the ratio of those two numbers, you get a number close to 1.6. And if you do the same with seed heads in a sunflower, the scale, of course, is very, very different from the scale of nanometers and atoms. We're now talking about millimeters and centimeters. But sometimes these patterns seem to be universal in the sense that they apply both at the very smallest of scales as well as the very macroscopic scales. And trying to understand exactly why that is an area of active research. But one of the weirdest results came out fairly shortly after the STM was first put into service. And this particular image shows it nicely. It's clearly a false color image, but the three-dimensional nature of what we're looking at gives you an idea that because we've got a ring of mountains here, it looks like we've got a ring of particles, a ring of atoms that are forming a sort of corral. So in this particular case, these mountains here would indicate that the atoms are sort of behaving like particles, because we can quite clearly see there's a mountain here and a mountain there and a mountain here and a mountain there, etc. But what's going on inside the corral? Well, if these are atoms, there should be atoms and electrons inside the corral. But instead of getting individual mountains dotted around here, we seem to have what looks for all the world like ripples in a pond. If you had a circular pond and you threw a stone in the middle, this is the sort of picture you would expect to get. So this image of atoms on a surface seems to simultaneously tell us that atoms are behaving like particles, and inside the corral it seems to be telling us that atoms are behaving like waves. So we have wave-particle duality in a single image, which is quite stunning in itself. Bohr's famous comment, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it." Because quantum mechanics is always flying in the face of common sense, you always have to stop and ask yourself, what is actually going on? And if it's disagreeing with common sense, do I reluctantly have to give up on common sense because it just doesn't seem applicable? One of my favorite quotes from Einstein, "The most incomprehensible thing about the world is that it is comprehensible." Quantum mechanics has been with us for 100 years and appears to give some really weird results. However, despite it being really weird, it is still possible to comprehend the world of the very, very small. In much the same way that although general relativity produces some rather odd results, it is still possible to comprehend the universe on the very largest of scales, as well as the very smallest of scales. And remember, there's no particular reason why the universe owes us anything. There is no particular reason that this particular monkey called Homo sapien should be able to comprehend the world on any scale. I like this image. It's not one of mine, but I like this image simply because it shows us the scale of atoms. This image is less than 1 nanometer on a side. It's 850 picometers. And we would interpret each of the blobs here as being an atom. What else would we assume they are? They seem to be spaced at the sort of interval that we would expect for the sort of things that we understand and the sort of things that we label as atoms. But it's very sobering to remind ourselves that if this image is an image of a few atoms, on the same scale, a grain of sand would be about the size of the moon. And that's what I tend to think about whenever I look at any scanning tunneling microscope image which purports to show a few atoms. We're looking at a tiny part of what would be the size of the moon for a grain of sand. And that's why I always go back to thinking about William Blake. To see a world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Thank you all for listening.
Thank you so very much. That was an amazing talk. Always humbles me incredibly whenever I see anything to do with quantum mechanics, especially when I saw my quantum mechanics exam results from undergraduate. They definitely humbled me. But thank you very much. To the audience, still, we'd love to see your questions. So questions are at sitp.online/ask. We'd love to hear some more from you. Please don't forget, we still would love to have some more donations to help other people come to QED. That's sitp.online/donate. And we will be back for the question and answer session at 8:15. And before we go there, I would just say, never ask a physicist to see their pet, because you never know what sort of state it will be in when the box is opened. So thanks very much, and we'll see you at 8:15. Thank you very much. And welcome back. Thank you very much. Well, glad to see you all back after the break. And we're now back with your questions. The first question we have is from a Dave J. No idea who that might be, but let's find out. Dave J asks, although all the non-mathematical descriptions are wrong, do they have a place in education as the stepping stones towards the maths?
Absolutely. You've got to accept that when you try and teach anything to anybody or explain anything to anybody, you can't launch headlong into what you believe to be the correct, rigorous explanation. You have to start with something that's appropriate for the audience. So if you want to talk to school kids about how the world is put together, you don't launch into the quantum mechanical maths. You try and paint the picture. Along the way, you probably have to say, this is not really what it's like, but the closest analogy, the closest picture we've got is this one. And it's wrong because of this, but it's the best we've got. And yes, you absolutely have to shoehorn in using pictures, using words, and only when they're ready do you hit people with the maths and say, this is the way it actually is.
And then they realised that they weren't ready for the maths, because you never quite are. And who was it that said, somebody once said all models are wrong, but some are useful.
That's a fairly good quote. Yeah.
And sort of the lies to children kind of thing. But that's a great question. Thanks from Dave. Now we've got a question from Paul, who is also known as Pictacule. I've never said that right in all the times I've done this. Does the granular nature of matter have a defined limit, Or are there particles composed of smaller particles, and so on ad infinitum? Is it particles all the way down?
This is effectively the so-called standard model. And we've been trying to understand what the world is made of for quite a while. So we got down to atoms and we thought, great, we now understand what the world is made of. It's made of atoms, which comprise a nucleus and electrons. It was realized fairly early on that electrons are fundamental in the sense that you can't take an electron, cut it in half and see what it's made of. But you can do that with a nucleus. So yes, you can go further on a deeper dive with the nucleus, and you find that's made of protons and neutrons. And that's not the limit, because you can take a proton and you can do a deeper dive and find that they are made of quarks. At the moment, we don't know how to go any further than that. In other words, you are made, as best we can tell, you are made of quarks and electrons, and to the best of our knowledge, quarks and electrons are not made of anything else. They are not divisible. So in that sense, they are the atoms in the original meaning of the word. But it might be that we simply haven't done the right experiment. It might be that quarks are made of something else, and eventually we'll find out what, and we'll cut them open and find out what's inside. But there are reasons with our current level of understanding to believe that quarks and electrons are, if you like, the fundamental building blocks which make atoms, which make molecules, which make us.
I'm gonna jump in on that one, because this is the thing I've never understood myself. Are quarks, according to the theory, are quarks made of strings, or strings are different? Am I looking at that the wrong way?
You're conflating two different things.
Good.
People who believe in string theory basically say there are no such things as particles.
Okay.
There are only strings. And it's so in other words, you can get things which appear to have particle-like properties, but they are actually strings. And so you could argue that in a sense, all particles are made of strings if you believe in string theory. If you believe that string theory is right, then strings are everything. And we only think that we see particles and waves because of particular properties of the strings in question.
Okay, thank you. Now a question from Igor. Another question from Igor. What are the chances that all this weirdness that we've talked about is just the result of us not understanding something fundamental about the universe? Or I'm going to add to that myself, is the weirdness itself the fundamental thing about the universe?
Yes, it is possible that it's weird because we've missed something. I mean, let's face it, when we look at the universe, we suddenly realize we've missed dark matter and missed dark energy. What an admission that we've missed 95% of the universe. So absolutely, we could be missing something. But I think the main point is that quantum mechanics is weird in the sense that it disagrees with common sense. But why would you expect something at the atomic level to agree with your common sense, which is only common sense because you've built up 18 years of prejudice based on this is the way things behave? In other words, I don't walk through a wall because that is not what common sense is all about. But if atoms are able to go through solid objects because tunneling is a real thing in quantum mechanics, is there any reason why you would expect it to behave the same? So it's only weird because it is so different from common sense. If we were brought up on a different, in a different way of thinking, if we were brought up in a world in which we could see atoms, then they would not be weird because they would be part of common sense. That's how atoms behave. It's only weird because we've discovered quantum mechanics recently. We've had 500,000 years of evolution to get used to the idea of, is that lion going to eat me? Where's the next meal coming from, etc. We've only had 100 years to get used to the idea of this is the way atoms behave. Maybe in another 500,000 years, we'll have been thinking about it so much that it will be perfectly natural and it won't any longer be weird. It's only weird because we're not used to it.
Yeah, there's been evolutionary pressure to understand things at a Newtonian scale. There hasn't been any evolutionary pressure to understand things below that. we can only hope that there might be evolutionary pressure for physicists to take over a bit more. I think there's also something said. There's a certain amount of arrogance that says our brains should be able to understand this.
Yes.
We're lucky to get what we can, I think.
Yep.
I'm going to go to a question now from Igor. Another question from Igor, actually. Oh, no, sorry. Okay, well, this is going to challenge you, I think, this one. This is a question from Paul, a.k.a. Picticule again. Can you give us a quick and dirty explanation of quantum computing? I think that's a no, but...
No, I don't think I can give a quick and dirty explanation, but it's very roughly, it's based on the idea of Schrödinger's cat, in the sense that things can exist in more than one state. In a standard computer, a bit is either 0 or 1. There's no in between. It's either one state or the other. And generally speaking, a computer works by jumping bits between state 0 and state 1. In a quantum computer, that goes out of the window, because in a quantum computer, you are allowed to have bits of the computer that exist in two states at the same time. How you apply that in practice to doing a calculation is very difficult to explain without maths, in my opinion. I've not heard a good explanation in English words that explain how that works. You can write the maths down and say that's what we do, but trying to come up with a nice, quick and dirty explanation, I don't think I can do that on the spot. No.
Okay. Again, Igor, our favourite question provider. Okay, this one's interesting. Do you have a favourite unified field theory? And does it even make sense to look for one?
I can't say I have a favourite. I am very much a pragmatist, in the sense that if anybody has a theory which sounds fantastic, I am very sceptical of everything. And I need it to be shown to me in a manner that I can understand. So if somebody tries to convince me that string theory is the theory of everything, I will probably just walk away, because I don't think it's within my comprehension on a short time scale to understand what it is they're saying. And you cannot reduce these things to a soundbite. I think you have to have a certain level of competence in dealing with the way these theoreticians build these field theories and these string theories and these quantum loop gravity theories. And I am not sure I have the time or the inclination to get there. So no, I don't have a favourite.
Okay. I'm going to expand on that a fraction. Do you have a particular interpretation of quantum mechanics that you like the most? And it doesn't have to be that you believe is true, that you like.
Of the various ways of thinking about quantum mechanics, I much prefer sort of collapsing wave functions than multiverses. I think multiverses get very expensive on universes if you have to divide the universe every time an electron decides that it's spinning that way rather than spinning that way. My limited brain cannot cope with the idea that the universe splits every time a decision is made. And I can just about get my head around the fact that a wave function collapses, though I'm still not entirely happy with that. I think I probably fall into the shut up and calculate brigade of quantum mechanics seems to give the right answers. I've been using it for the last 30 to 35 years, and amazingly enough, it seems to work. And occasionally I worry about why, but most of the time I don't.
Okay. Next question. Okay, that's not particularly nice one, so we'll move on. Malcolm asks, you say that in an atom, an electron could be absolutely anywhere in the universe. How does that interact with the limit of the speed of light?
If you make multiple measurements, in other words, if I were to take a particular system and make a measurement, and then make another measurement, there will be limitations on how far it could have travelled in the meantime. So in other words, it's back to this idea that you just asked me. If you make a measurement, then in a sense, the wave function collapses, and then you do definitively know, because I've just measured it, the electron is quite definitely here rather than it could be anywhere. As soon as you've said, right, I now know it's there, then there are limitations placed on where it can be next time you measure it. But in the absence of an initial measurement, then basically one arbitrary measurement, in principle, the electron is not constrained to be anywhere in particular.
Okay, thank you very much. Let's have another one from Igor then, since he's been so eager today. Oh dear, that sounds terrible. Are the talks about multiple dimensions of any merit in this conversation? Do we have a better framework than the dimensions, man? All 28 of them.
It comes back to my earlier answer. I don't like the idea of having more than 4 dimensions. I've got no idea if that's right or wrong. I just have great difficulty in trying to live in such a universe. Separating is that the universe we live in, or is that a mathematical tool that allows us to get the right answers if you assume that we're living in 11 dimensions? Is that sidestepping the issue? If the maths tells us that you need 11 dimensions for it to work, is that telling you something fundamental about the nature of the universe? Or is it telling you that you've just actually found a very useful tool to tell you about the 4-dimensional universe? I'm not clear about which of those two actually hold.
Let's not multiply entities without need.
Occam's razor. Yes, that's right.
Remember to vote in the Occam's razor, folks. Website available in the chat. Okay, I'm being bullied by the Slido, so I may as well do this one. If quantum mechanics says reality isn't real, does that mean that Bremner, myself, doesn't exist? And I think she's hoping you say yes.
Yes, clearly.
Okay, thanks very much. Okay, next one. From Karen Tankerus. How unified are the quantum and Newtonian worlds these days, in your opinion? So-called unified theory has been the aim in physics all her life.
Unifying Newtonian physics with quantum mechanics is not really the problem, in the sense that if you scale up quantum mechanics, it must give you the same answer as Newtonian mechanics, in the sense that if you say, well, this ball is moving at a particular speed on the billiard table, if I were to solve that with quantum mechanics, I can't get a different answer because I know that the ball is moving with that speed. So quantum mechanics must give me the answer of Newtonian mechanics. The problem with unified field theories and virtually every theory of everything is getting quantum mechanics to work with general relativity. They are not good bedfellows. But in principle, scaling up quantum mechanics beyond the nanometer, beyond the micron, even beyond the millimeter, is not necessarily an issue. We do have ways of interpreting, and we do have problems with understanding the nature of how things hold together and why we don't see quantum effects in the macroscopic world, but that doesn't mean that quantum mechanics still underlies everything in Newtonian physics.
We know, for instance, we use quantum mechanics determines how our computers work. We know computers control planes. The two have to be unified.
They can't give different answers. Otherwise, we wouldn't know what on earth to do.
Next question is from Andy, who asks, if magnetism is an effect of special relativity, what's an electromagnetic wave? And do photons travel instantaneously from their point of view? And finally, this is a lot of questions all in one, is time caused by entanglement? And you can take those in any particular order you like.
Last one first. Is time caused by entanglement? I don't know what time is. Therefore, I can't answer that question. What's the middle one?
The middle one is, do photons travel instantaneously from their point of view?
Via the most interpretations, yes. As far as a photon is concerned, time does not exist.
Okay, and the first one, if magnetism is an effect of special relativity, what's an electromagnetic wave?
An electromagnetic wave is effectively a disturbance in the electromagnetic field, that probably sounds like a totally circular argument. But if we assume that fields are all pervasive, then basically the existence of a photon is simply an excitation of a particular field, which we call the electromagnetic field. So that's one way of looking. That's the field theory way of perceiving the universe. Everything is fields, and some of those fields have excitations, and then we can identify that's a photon, that's an electron.
Okay. I'm going to move down a little bit just so Dave knows what I'm doing. I'm moving down a little bit to another question from Andy Wilson this time. Fantastic talk. Thank you. I'd like to second that. Are all electrons the same as one another? And I'm going to add, is there more than one electron?
Possibly. I don't know. The idea that it's the same electron that's just very active, I find it difficult to get my head around that concept. So I would prefer to think that there are lots of identical electrons. Why they're identical? Who knows why, but they appear to be identical. If they're identical, we can't tell them apart. So how do we know they're not the same electron? The answer is we can't.
The next question is, I'm going to preempt the question from Karen Tankerus that I know lots of people wanted to ask. We have been asked, do you have a pet? We already know the answer, sadly. There is no pet for us to see. The experiment went the other way. No, he never did that. That's cruel. I shouldn't have said that. Igor asks, similar to another question, but I think it comes to an interesting one, slightly different one. How small can we go? And what's beyond very, very small? Is there very, 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 very small? Or is there a void of emptiness at some point? So I'm going to ask, can you expand a little bit on what is the smallest amount of stuff we can have in terms of quantum mechanics? Or not even stuff, but amount of space we might be able to have?
Quantum mechanics as a mathematical construct does not have limits. So within the construct of quantum mechanics, we have point-like particles that have no size. So technically they are zero-sized objects. Whether they actually have zero size or not, the point is we cannot measure them. We cannot measure the size of an electron. If an electron had size, that means we could cut it in half and find out why it has size. So it links to the question of, are they fundamental or are they made of something else? That's slightly different from saying what's the smallest thing we can possibly think of, because there are reasons to believe that it's difficult to keep our laws of physics on scales smaller than the Planck length, 10 to the minus 43 meters. In other words, it's difficult to see how we can construct anything on smaller spatial scales or smaller temporal scales than the Planck time and the Planck length. But that is just an assumed limit. There's no proof that that is actually a fundamental limit.
Does that, sorry, this is again me having not done very well at undergraduate relativity and quantum mechanics. Does the Planck length not come out straight from the uncertainty principle, though? Is that not? It doesn't just fall out from
No, the uncertainty principle tells us about the relationships between various properties of various either particles or waves. Planck comes from an argument which is, if you take all of the fundamental, what we consider to be the fundamental properties of the universe, such as the speed of light appears to be a fundamental speed limit, the gravitational constant appears to be something fundamental about how space behaves with time. If you take all of those constants and throw them in the air and see how they land, you end up with a Planck time, a Planck mass, and a Planck length scale. And because you can generate a distance, a time, and a mass, people consider, well, the speed of light must mean something. The gravitational constant must mean something. If you throw them together and get these numbers, they must have some meaning in our universe. So that's a sort of valid thing to do, but I don't think it necessarily proves that that is the smallest thing, the smallest time, etc. I mean, for instance, the Planck mass doesn't come out to be the smallest mass you can comprehend. It comes out to be something quite macroscopic.
Okay. We've got another question from Dave J again, and I'm going to add to this one as well. Who do you think had the biggest impact on quantum mechanics overall?
That's difficult because I showed, I don't know, half a dozen people, but in fact there were dozens of people who all made a contribution. And each of them, like Newton, stood on the shoulders of giants. They all took ideas, discussed amongst themselves, and developed, sometimes individually, sometimes in groups. And all of them kicked ideas around between themselves. So Einstein borrowed ideas from other people before he came up with his ideas. Max Planck, Bohr, etc. They were all important architects, and Schrödinger and Heisenberg were by no means the only people who constructed quantum theory from the work of everybody else. So no, I find it difficult to pick out one person who is the linchpin of quantum mechanics. It was quite definitely a dozen different scientists, of whom I've only name-checked a few of them there in the slide.
I'm going to expand on that just a little bit. Would you think it's fair, and this is a thought I've had in the past, that the first 50 years of the 20th century may have been the most productive or most revolutionary period of that shorter period of time in terms of
I would argue the first 30 years. In other words, quantum mechanics wasn't settled by 1930, but it was all but there. And given that at the end of the 1800s, people were saying, well, there's no more to physics, is there? We've found everything, we've got everything. We just need to, to finish off some of these decimal places in the measurement of X or the measurement of Y. And there's no more physics to be learned. A lot of eminent physicists were saying that. And then 30 years later, we've got special relativity, general relativity, and quantum mechanics, all essentially over that 30-year period. So I would argue those were revolutionary times, and I'm not sure we're ever going to see 3 decades like that again. Maybe we do need that sort of change, literally a paradigm shift from where we are now.
Something to combine the big and the very small, the fast.
That's the sort of thing we need, because people are not making headway at the moment, I believe, between general relativity and quantum mechanics, and we need something like the mindset of 100 years ago to kickstart a new revolution.
Okay. Our final question comes again from Skeptical Gumby in Oxford. According to Einstein, time and space are the same. And if quantum mechanics is true, does that mean that Douglas Adams was correct when he said that time is an illusion and the time for us to finish is equally?
Lunchtime, doubly so, absolutely. Yeah, I would agree with that.
And as I tweaked quite a little bit, and that is unfortunately the end of our time we have today. So everyone in the chat, please, once again, do the emoticons, do the clappy symbols that you do. And thank you very much to Dr. Stephen Barrett. Thanks very much indeed.
You're very welcome.